We're going to keep up the pace but sort of change direction a little bit. We're going to go back to some basics. As Steve said earlier, fire dynamics is taking chemistry, fire behavior, materials analysis, things from mechanical engineering such as heat transfer, fluid mechanics, and putting them all together to understand fire behavior. Now, the first textbook in fire dynamics wasn't written until 1986. So this is a relatively new science. This is a relatively new area of study. That textbook, needless to say, wasn't written for firefighters, right? It was written for other engineers, other scientists, other researchers. So now we finally advanced to the point that there's been an area referred to as the golden age of fire science, if you will, that sort of ran from the late 60s, starting with the Home Fires Project at Harvard University, got into the creation of the Center for Fire Research at NBS, which is now NIST, where I work. And some people say it sort of ended around the late 80s, early 90s. And it basically took that amount of time for them to really understand a lot of physics regarding the fire in a single room. And now we're getting a better understanding as the technology advances with both fire modeling and fire experimentation, understanding fires in full structures, and actually going out and running tests with the fire service to understand the fire dynamics of fires in full structures. So what is a fire? Well, for one thing, you can't burn a solid and you can't burn a liquid, right? So the reason is because the fire is a gas phase chemical reaction. And we say it's exothermic, which means it gives off heat, it gives off energy. And we say that it's an oxidation process, which means that it requires oxygen to generate that energy. If there's no oxygen, there's no chemical reaction, there's no energy given off. Everybody knows about the fire triangle, the fire tetrahedron. We need fuel, we need oxidizing agent, we need heat, and then we need this chemical reaction, this self-sustaining chemical chain reaction that needs to keep going to generate sustaining flames. Everybody was in the class this morning. We talked a little bit about your traditional fire behavior where the graph on the left ought to be pretty familiar, where you have ignition, growth, fully developed. You might have flashover or a backdraft right at that bend for the fully developed stage, and then decay. And that's typically driven by fuel. Then we have the ventilation controlled fire. And that's more typical of the fires that you're going to encounter on the street today, unless the homeowner leaves doors open or something when they leave that fire area. But again, with the changes in insulation, the desire to keep as much of when we're normally heating or cooling our homes, we want to conserve energy, right? We want to keep the heat in or the cool in, whatever we're producing at that season of the year. Well, the result of that is there's not very much air exchange with the outside. So it means there's not going to be a lot of leakage. Once a fire starts in that house, it's going to hold all that gaseous fuel inside. So smoke is fuel. I have to click this one. Easy demonstration, you can do it at the kitchen table. Take a candle, blow it out, bring the match to the gases that are coming off the candle wick, and you'll see the flame goes back to the wick, right? Smoke is fuel. What's in that smoke? Well, we have basically that glow are carbon particles under a high state of energy that are beating and banging against each other and glowing. And if we cool them off by having them condense out on a piece of metal like a spoon, what's going to happen to the spoon? It's going to get sooty, right? So that's the fuel that's contained in there, giving you a representation of some of the fuel that's trapped in there that'll burn. So solids don't burn, liquids don't burn. If we want to have carpeting or a sofa or a wood piece of wood burn, we need to pyrolyze it. Fancy word. Just means we're applying heat to this thing, and due to that heat alone, it's breaking down the materials into a gaseous fuel. If you only take one video home to show them, well, I guess two. The Steve's comparison video is a pretty telling video, and this one for fire dynamics sort of shows everything you need to demonstrate. We've got a dry Christmas tree in a 12 by 12 living room with some furniture in there and an open doorway. Notice how the excess fuel is spreading across the wall and how the flames start to follow that fuel down, right? That's the fire triangle in action. hot gas, oxygen, and fuel. Next, we're going to see the radiant heat transfer from the flames start to pyrolyze the sofa and the chair. So we have blue polyester covering on the chair, and you see it turn into a white vapor. That's raw fuel. That fuel's going up into the upper layer, the hot gas layer. The hot gas layer starts to burn. We have rollover. The radiation from that starts to pyrolyze the carpet and every other fuel that we have in there. It's going to entrain a lot of oxygen through the doorway. There's going to be very turbulent mixing, and we're going to transition a flashover, and then that room's going to do what? It's going to start to darken down because it doesn't have enough oxygen inside to breathe. Where's the fire? It moved outside that open doorway to be a 8 to 10 foot tall flame outside that doorway because it can't breathe in there. Heat transfer. So what were the conditions inside? What if you were inside that room? Could you survive? Probably not. Sometimes you hear people talk about this condition referred to as black fire. That's when the gases are hot enough to be flames, but they don't have the oxygen to burn, and they're getting pushed or moving through a structure. So heat transfer. Without heat transfer, you can't ignite anything. You can't have fire growth. At the same point in time, if you put water on something, if you don't have heat transfer, you can't have the fire go out either. So heat transfer is very important. Again, basic physics. There's some laws of physics here. Heat transfer only goes in one direction, from hot to cold. Right? Mechanisms of heat transfer. Again, firefighter 1 type of stuff. Conduction, convection, radiation. Conduction is heat transfer within solids. Convection is heat transfer between gases or between liquids and gases or gases and solids. So for example, when the fire plume goes and hits the ceiling and turns into a ceiling jet, those gases are rolling the ceiling. It's transferring heat to the ceiling via convection. Radiation is heat transfer by light energy, so you have to have line of sight. So if you're not directly between the emitter, whether it's the flame or the hot gases overhead, you can shield yourself from the radiation. Basically, if you're standing out in the sun and you step into the shade, right, you got out of the direct radiant light from the sun. Same kind of thing. Showing you a few, not all equations, but a few so you understand the process. So this is convection. So that Q dot in scientist lingo is heat rate, heat transfer. And it equals a convection heat transfer coefficient, H, times the difference of T hot versus T cold. So in this particular case, T hot are the gases coming off that fire, and T cold is the initial wall temperature. And then the last thing we multiply by is the area of the target, or the area of the wall. Now that wall could be you and your turnout gear, right? You could be the target for that heat. So one thing you notice right away is that TQ, or Q dot, is going to be bigger if the difference between T hot and T cold is bigger, right? So if that difference, instead of being, let's say you were 70 degrees when you went in there and the fire environment's 150 degrees, well, that piece in between would be 80. Well, if it's 400 degrees in there and you were 100 degrees by the time you got there, now that interior piece, our delta T, is going to be 300 degrees. So you can see a direct relation there that if you go into a hotter room, the heat transfer between you and the hot gases in that room is going to be larger. Now here's the part that might not be so intuitive, and that's that H factor. And the H factor is basically how turbulent that gas flow is across your body, how fast it is. And so if you have a laminar flow, not very well mixed, very slow, we might multiply that delta T by 5. But if you have a high flow rate, high velocity, well-mixed, churning gases that are going over you, now we might multiply that delta T by 50 or by 100. This is basically the equation. You may be more familiar with wind chill, right? When you go outside in the wintertime, they tell you, well, the gas temperature, the air temperature is 40 today, but we got a 20-mile-an-hour wind. So when you go outside today, it's going to feel like 28. That's this equation, basically. So why does it feel like that? Because the rate of heat transfer to your skin is faster than your skin can keep up with heating your skin. Whoa. So molecules of air, cold molecules are coming across your hot skin, right? Hot goes to cold. It picks up the heat and moves on. As we increase the wind, just as we increase the air velocity, more cold molecules are hitting your skin and taking away more heat. And as a result, your skin cools down because your body's not creating enough heat to keep up. So you feel colder. Well, now when you're in a fire environment and hot goes to cold, you're probably the coldest thing in that fire environment. And now if we put hot gases with a high velocity over you, now it's more like having the hairdryer at home, right? You turn it up on high, you move your finger in front of the nozzle, and it feels a lot hotter than when it was on low, right? You're increasing the heat transfer rate. So the air temperature didn't change, but the amount of air going over your body changed, and as a result, you're getting hotter and your gear can't protect you for as long a time. So again, when we have forced convection, it could be anywhere from multiplying that delta T by 10, and 500 is sort of the rear end of a jet engine. So I mean, that's another extreme. But the key thing is, if that Q dot gets bigger, it's not good for you. How else might we use this? So I mean, this is a good thing to kind of keep in mind. Let's say that you show up at a fire training event, and some person, could be an experienced person, could be a scientist you never heard of before, says, you know what, I think the best idea is when you've got flames rolling the ceiling, let's put the water on the floor. I'm going to show you. We're going to go in this 20 by 20, this 20-foot sea tainer, and look, the flames are rolling the ceiling, and I'm going to get down here, and I open up the hose line, and the water goes on the floor, and the fire went out. And you might walk away saying, damn, fire went out. That's pretty neat. Well, that was in a sea tainer, right? Let's look at the physics. If you want to increase your Q dot, if you want to increase your heat transfer, where do you want to put your cold water? You want to put your cold water in the hottest places possible. So if you've got 1,800 degree flames up here and 400 degrees down at the floor, where do you want to put your water to make the most sense? Right? Get it in the hot stuff. Now, that said, if you've got a small room, maybe it doesn't so much matter where you're going to put the water. Just get the water in there, right? But just something to think about as you hear different things over time. Convective heat transfer, back to the candle. If we take a candle and we make a measurement over the candle, you see our sensor there is within about 1 inch of the candle flame. As we move the sensor over the center line of the candle, we're seeing 80 to 100 kilowatts per meter squared of energy, which is why you can light many things on fire with just a small open flame. Very close to it, right in its center line, has a tremendous amount of energy. So let's sort of look at our threats, our hazards. We have a early growth stage fire showing there. There's a open door where fresh air is coming in behind the firefighter, and radiant energy, a little bit's coming from the chair and some is coming down from the hot gas layer. That's transferring energy to the firefighter. Convection, again, early stage. This is sort of the ideal situation here, where the convected air that's coming in the door low is actually cooler than the fire environment inside, and that's helping take some of that heat that was transferred by radiation away from you. So that's a good thing. But notice where the high heat, high pressure gases are exiting out the top. So one might imagine that if you were to be in where the red arrow is, that could be bad, right? The heat transfer to you is going to be increasing. So if the hot gas layer comes down to where you are and is flowing over you, you're in trouble. Conduction. A lot of times we just think about conduction being, where you're touching something, where you might be your gloves on the floor or on a hot surface, or your knees crawling on a hot floor. But the other thing to remember is, how does your gear protect you? Your gear protects you by absorbing energy and storing it. And then what happens? The gear gets pretty hot. What direction does heat flow? Hot to cold. What's the next cold thing? You inside the gear. So at some point in time, that's the gear that's touching and pressing against your skin is going to be conducting through that gear into your body. So when your gear's hot, the last thing you want to do is have it compressed against your skin. If one of your fellow firefighters gets his trim on fire and you have this temptation to pat it out to put the fire out, you're really not helping them, right? You're going to push the hot gear against the skin, make the burn injury worse. Cool them off. Throw water on them, get the gear off. You got to get the heat moving away. You want to change the direction of the heat from going to him to somewhere cooler to going away from him. Firefighting thermal environments. So in the green box there, on the bottom we have heat flux, kilowatts per meter squared, and that's again this radiant energy. And vertically we have air temperature, which will control our convection heat transfer. So we've got convection on one side, radiant heat transfer on the other side. And the key thing to remember is that these two sources of energy from the fire add up, right? If they're absorbed in your gear, they add up. So routine case, 1 to 2 kilowatts per meter squared, and up to about 160 degrees Fahrenheit is sort of the routine case. That means your gear can protect you probably for on the order of 10 to 15 minutes under those type of steady state conditions. We get into the ordinary case, and that starts at our sort of 2 kilowatts per meter squared and 140 degrees Fahrenheit, and goes up to a peak of 400 degrees Fahrenheit and about 12 kilowatts per meter squared. Once we get to that upper corner of ordinary, now you're sort of in that kind of 2-minute range of protection. And once you get, again, but part of this depends on how hot were you before you got in that condition, right? And then we have the emergency condition where we're kind of considering that less than a minute, right? You need to be making your way out of that space or changing the condition of that space pretty dramatically under those sorts of situations. So I'm going to show you a couple of films here. We have a chair that weighs 42 pounds. I've got 2 of them in there, polyurethane foam and polyester batting. And here I've got 1 window and 1 door to this compartment that's about 12 feet by 10 feet by 8 feet tall, and the door and the window are both closed. And you're going to watch the fire develop. You're going to watch the smoke grow. And just under the window you saw a couple of squares on the wall. That's firefighter turnout gear that we have instrumentation in. So the smoke layer comes down over the firefighter turnout gear. What's happening to the fire right now? Starting to run out of oxygen. The hot gas layer is coming down below the level where the fire can entrain fresh air. So if we don't do something quick, that fire is going to go out. It got hot. It started to build a little pressure. Smoke started to force its way around the cracks in the doors. You see it pushing out there a little bit. So we're going to open the door. The fire was still in the early growth stage, right? So as a result, what happens? Opening that door works. Hot gases are going out the top. High pressure hot gases going out the top of the door, and fresh air that's at lower pressure gets entrained, basically pulled in by the fire into the lower level. What do you see happen? The smoke layer lifted. You could see, you know exactly where the fire is. I've slowed the video down to real time, and watch the lower right-hand corner, and we're going to start to see rollover. And when you see rollover, you're going to notice the flames are going to go across, break the interior pane of the double pane window, but not fail the window totally. Notice that the flames are going to burn at the interface of the hot gas layer and move toward the door. They're going to move toward the source of oxygen. And you see how the radiant energy increases, pyrolyzing the carpet as it does that. And now we're going to sort of stop it just short of flashover by hitting it with a sprinkler. So here we have a graph. I'm going to show you a number of graphs. So basically we've got the temperatures starting from 1 inch below the ceiling, the blue line. Then we come down a foot, and then they're every foot until we get to 1 foot above the floor, which is that sort of neon green line. So you can see that we got to temperatures on the order of 300 degrees Fahrenheit, 1 foot above the floor, within about 3 minutes of ignition. So what's that tell you about occupant viability if somebody happened to be stuck in that room? Not very good. Notice how the temperatures drop off a little bit until we open the door. Now notice what happens to the graph once we open the door. The conditions separate, right? And you saw it in the video. We once again have a hot gas layer and a cool lower layer. So the temperatures 3 feet above the floor and down, where you would be crawling, are ambient conditions. They're 100 degrees, just as it was that day when we were running the test. That's the outside air conditions that you'd be exposed to. And life is good, perfect working environment, fully encapsulated in your gear. You're well protected to work under those conditions. You have about A little bit of heat flux hitting you less than 5 kilowatts or so. Life is good until what happens? Until rollover. Once that rollover occurs and we've got flames rolling the ceiling, the radiation kicks up, the convection keeps up because the hot gas layer comes down, and you see how rapidly conditions change. We go from you being in a safe environment to you being in an untenable environment in about 20 to 30 seconds. So there's a measure of total heat flux, which is convection and radiation added up. That's the blue line, and the green line is the radiation alone. So we get up to 50 kilowatts per meter squared very quickly. Now your gear is tested to what level? Anybody know in the TPP test? 84 kilowatts per meter squared. Any idea how long you would be safe or how long you should have before a second degree burn injury with a TPP rating of 35? In theory? 8 seconds? In theory it's 17 seconds, but you know, if you assume it's compressed a little bit or dirty or you know, you got a little preheated before you got there, the key thing is you don't have a lot of time. Right? You've got to be moving. If flame's impinging on you, you've got to be moving, and you can see how quickly those things change. Here's the temperature of the PPE that was on the wall. So the outer layer temperature was sitting at about 200 degrees, and the inner layer temperature, the green line, is a little bit less. So assuming you have a station work uniform and you're centered in your gear, right? Keep the hot gear off you a little bit, you're going to be working in there. You can be okay. When you see them both make that vertical turn, that's sort of your safe time, a little less than 20 seconds, between when the blue line turns north and the green line turns north, and then you're burned. Heat flux inside the gear, same kind of story. So now we're going to look at, again, similar room, same kind of fuel load. We've got a 40-pound chair that we're going to ignite to start with. Again, you're going to see the thermal plume go up. We're going to see the ceiling jet go across the ceiling. When it reaches the walls, it starts to form the hot gas layer. That hot gas layer, which is now a reservoir of fuel, continues to be heated, and more fuel is added to it as the chair burns very inefficiently. We've started out with an open door, so do you think it's going to go to flashover faster or slower? Slower because it's letting heat out, you think, right? Actually, it's going to be faster. Right, because it's got that continual supply of oxygen, right, to feed the fire. So we're going to slow it down to real time again so you can watch the rollover. And notice when the convective layer goes over the turnout gear. Right now it's just hanging a little above the turnout gear. We have our rollover. So at about 180 seconds, 200 seconds is when that turnout gear starts getting bathed in hot gas. Notice how the flames are going toward the door. Now this one we're going to allow to transition to flashover. Look at what the smoke looks like from the outside. Notice where the neutral plane is. The difference between the high pressure hot gas layer and the cold fresh air going in the door is lower than the base of the window. So the window is unidirectional, high pressure pushing out top to bottom, and the door is our only air inlet. What you see there, that pulsation of fire, you might consider that pushing fire. That's ventilation due to how it's getting the oxygen in to mix with it, and when it can burn it, when it can't burn. Basically, we need the fuel to lean out a little bit before we get flames continuously out of that window and out of that door. Is that a hard fire to fight? Not from the outside. Right? So fires like that, in previous cases, we've introduced, let's say, 2 gallons of water by throwing a bucket in the window or in the door. It darkens the fire out for a short period of time. If you don't have another bucket of water pretty quick, it's going to come back like a banshee in no time. But again, the fire can't breathe. That's why the flames are moving out of the door. It's very fuel rich, and introducing some water into the compartment while the fire's still trapped in the box, so to speak, is very, very effective. So there we see our thermal gradient, our temperatures again from the floor, from the ceiling down to the floor. Initially we have temperatures at the ceiling sitting around 390 or 400 degrees. Near the floor they're ambient conditions until we have rollover. You see they rapidly increase until we reach post-flashover, which would be defined as temperatures in excess of 600 degrees C or 1100 F. That also happens to be the auto-ignition temperature of carbon monoxide. So we're sitting at temperatures floor to ceiling in that space around 1500 degrees Fahrenheit. Notice introducing the hose stream from outside drops the temperatures very quickly to about 200 F. Heat flux, again, now we're up to about 75 total heat flux. The radiant heat flux is up to about 30 because we allowed it to transition to flashover. The PPE temperatures, again, you're okay. The outer temperatures are below 200 degrees Fahrenheit. Inside the gear is less until we have rollover. So when did the hot gas layer come down over the turnout gear? At around 180 to 200 seconds. Well, there you can see it in the graph. Right? So as soon as those hot gases start impinging on your gear, your time of safety, of safe operating is gone. You need to be moving or changing the environment. Flow path. So basically, flow path is the volume in a building, a series of rooms or hallways or corridors or stairwells that's between an inlet and an outlet. So I got some gray hair in here, so some of you guys might have been hot rodding back in the day, right? So if you consider the fire structure as your internal combustion engine, and your inlet was your carburetor, and your outlet was your exhaust system, if you wanted to get more energy, more horsepower out of that car, what did you do? First time you got your check from working at Safeway or whatever, what did you do? You had to go get some hooker headers, man, and some glass packs. Got to let it breathe, right? Got to open up that exhaust. Got to get that Holley 750, you know. You got to get that big carb on there to increase the flow path. Make the engine a better air pump and fuel pump and let it burn better. Well, that's really what we're talking about here with the structure. Whether you want to use the analogy of an automobile or the analogy of a wood stove with the damper controlling the exit of the flow path and either the front door where you're loading the fuel in, it's the same kind of deal, except now we're talking about structures. And when we're talking about basement fires, if you want to use that analogy of the wood stove, now you got a wood stove that's made of wood. You're dancing on top of it, and you're going to open the damper and open the inlet and think things are going to turn out well. So that's really what we're talking about here.